Welcome to the second session of the JEE previous year question from the chapter Haloalkanes and Haloarenes. Let's go to the question directly. The increasing order of reactivity of the following compounds for SN1 substitution. Dear all, they're asking you SN1, which will undergo SN1 faster. You know what are the steps in SN1 mechanism? First, you remove the halogen. First, you remove the halogen and make the carbocation. What is the halogen here? Yes, remove the halogen, make the carbocation. Remove the halogen and make the carbocation, and you check what type of carbocation is this and which is more stable, dear all. Very simple. What type of carbocation is this? This carbocation, you can able to see it's directly connected to only one carbon and it is a primary, but there are two bulky groups, right? There are two bulky groups, right? It is a carbocation. What about this carbocation? It's purely primary carbocation. It's purely primary carbocation because the carbocation connected to only one carbon. But this carbocation is now it is primary. There is a chance to make it what? The other stable carbocation where more bulky groups are there, right? You know, more the bulky groups. Or what is this bulky groups are? Plus I groups. Electron donating group. More electron donating group on the carbocation, it become more stable. So compared to A and B, A is more stable because on the carbocation we have electron donating group, dear all. Electron donating group can increase the stability of carbocation. So A and B, when you consider, A is more stable than B. What about C and D? C and D, you can able to see the carbon cation on benzene ring. What is the carbocation on benzene ring? What we call benzyl carbocation. Here all benzyl carbocation, here also benzyl, here also benzyl. Both are benzyl, they are more stable than this primary. So C and D are more stable than A and B. Among C and D, which is more stable? Can you able to say? Among B and C, which is, C and D, which is more stable? Dear all, this both are benzyl carbocation where OCH3. What is OCH3? Methoxy group is an electron donating group. Again, electron donating group can increase the stability of carbocation. So C is more stable than D. So we can able to see C greater than D. Among A and B already we discussed A greater than, that is A greater than B. So the answer is BADC, that is option C, BADC. Why C is more reactive toward SN1, dear all? Where the benzyl carbocation is more stable due to the presence of an electron donating group extra. What about D? There is only benzyl carbocation. What about option A? There is some alkyl groups on primary. What about B? That's only primary. Next one, the major product of the following reaction is, you can able to see the given compound is CH3, CCH3, H, then CHBr, then one more CH3. It's reacting with which compound, dear all? CH3OH. What is CH3OH? Methanol. You know, methanol is a polar protic solvent. Methoxide ion is there. Methoxide ion is there. Methoxide, you know, it's a basic one, right? H plus and O minus. When you consider what is methoxide, it's a basic one. So when it undergo haloalkane react with a base, what happened, dear all? Beta elimination happen. What is beta elimination? Halogen we will take from alpha. Hydrogen we have to take from beta, right? But careful when you're doing all these questions, careful, dear all. When you remove the halogen from alpha, you will get a carbocation. Yes or no? When you remove halogen from alpha, you know, polar protic solvent. So Br, this OCH3, we need to substitute, right? Just like a substitution reaction, SN1, you know, in presence of polar protic solvent, SN1 mechanism happen. So dear all, here instead of the beta elimination, methanol is given. Methanol is a polar protic solvent, right? In the presence of a polar protic solvent, a haloalkane preferred to undergo which mechanism? SN1 mechanism. Polar protic solvent like aqueous alcohol medium. SN1 mechanism preferred, right? So what is SN1 mechanism? First step, remove the halogen, make the carbocation. Yes, we did the carbocation. Now at present situation, what is this carbocation? It's a secondary carbocation. Yes or no? Because the carbocation connected to 2 carbon. Immediately don't try to add the nucleophile OCH3 to this carbon, dear all. That's wrong. Please check it whether it's secondary, there is any chance to make it as tertiary or not. Now it is secondary. Please check it. You know, tertiary carbocation is more stable, right? Please check it. Any chance to make this secondary into tertiary or not? Is there any chance, dear all? Yes. You can able to see from the nearest carbon, this one, there is a hydrogen. If you transfer this hydrogen to this carbon, this is called what? 1,2 hydride shift. What we call 1,2 hydride shift, right? 1,2 hydride shift. To the nearest carbon, when hydrogen shift, when this hydrogen shift to this carbon, you will get the compound CH3, CCH3, CH2 and CH3. Now where is a new positive charge? Can you able to say, dear all? Here is the positive charge because H is leaving as H minus. Hydride shift. So now it is, initially it is secondary, now it is tertiary. Yes, dear all, please check it. In SN1 mechanism, if you get a compound with a primary or secondary, please check it by the hydride shift or methyl shift whether there is a chance to make it tertiary or not. Okay, so hydrogen if there, yes, we can shift hydrogen, we are getting tertiary carbocation. Now where the nucleophile OCH3 will attack, dear all, on this carbon, you will get the product as CH3, CCH3, OCH3 and we have CH2, CH3. This is the product. Yes or no? So where you can able to see this product, dear all, through SN1 mechanism, CH3, CCH3, OCH3, CH2, CH3, that is option C. Clear all of you? Simple. Next one. The major product Y. Where's the Y here in the following reaction? 2019 question, dear all. The given compound is, let me just do in the same question. What is the compound given, dear all? The reagent is given sodium ethoxide, right? Sodium ethoxide. No, I told you sodium ethoxide, these all are bases, dear all, strong bases. So in presence of ethoxide base, haloalkane prefer to undergo what? Beta elimination. What is beta elimination? Halogen go from alpha, hydrogen go from any of this beta. Which beta carbon you select, dear all, to take hydrogen? Maximum try to make the double bond in a more substituted area. That is say it's a rule. So let me take hydrogen from this carbon, dear all. So take halogen from alpha, take hydrogen from beta and make a double bond between alpha beta. So the product will be like this, dear all. You will get the product as double bond in this area. And there are two methyl group like this one, to which this is your compound X, on which what they are adding to this, they are adding HBr without peroxide. You know, HBr without peroxide is what? Markovnikov's rule. What is Markovnikov's rule says that? You can able to see this is just a C, this is CH, right? Negative part of the addendum goes to carbon with what? Less number of hydrogen, and positive part to got more number of hydrogen. So what you will get, dear all? You will get the bromine substituted over this carbon. So you will get this product CH3, CH2, C on which 2 methyl group and bromine. Where you can able to see this product, dear all? Yes, it's option C. So what's the first step, dear all? First step is beta elimination because there is a strong base with HBr without peroxide. It undergo Markovnikov's rule. We'll get this compound C as a product. Next. In 2020 question, in the following reaction sequence, structure of A and B respectively will be. It's a combination of alcohol chapter and haloalkane chapter, dear all. The given compound is, simple question, there is a benzene compound is given with there is an ether, and here we have CH2Br. Let me show the steps. Clearly listen, all of you. Clearly listen. First they are treating with HBr and heat. You know, it's an ether, it's an aromatic ether. Ether when react with HBr, you know, the carbon oxygen bond break, right? Either this CO bond or this CO bond break. Which CO bond break, dear all, in an aromatic ether? Remember, if it is an aromatic ether, just like consider one of the example, you know, anisole. What is anisole? Benzene with the OCH3. In this type of compound, remember, after the breaking of the CO bond, we should get phenoxide ion. What is phenoxide ion? Phenoxide means what? Benzene with O minus. After, when you treat a ether with HBr, if you are getting a phenoxide ion, such a way, try to break it, all of you. So let me break this CO bond because I will get phenoxide and carbocation here. To this O minus, O will attack from H plus and Br minus. To the O minus, H plus will attack. To the carbon, Br minus will attack. So we will get the product as the phenoxide to which O hydrogen already attacked. Here CH2Br already there. And what is next one? You have CH2, CH2, CH2Br. You have CH2, CH2, CH2 on which Br. This is the product you are getting. Where you can able to see this product dear all as the first one. The OH on this end, it's wrong. Not option A, not option C, either B or D. Where you can able to see that, yeah, this is the same compound you're getting here. And it's not over. This is your compound A. This on reacting with what? Sodium in presence of what? Ether. So what's the reaction dear all? This is our Wood's reaction from the chapter Haloalkanes and Haloarenes. This is from alcohol, this is from haloalkane. When you treat a haloalkane with a sodium at a dry ether, what happen? Wood's reaction will happen. What is Wood's reaction dear all? So see dear all, in the same compound you have two halogen. In the same compound you have two halogen that is taken by sodium, and these two ends connected. So you will get that benzene with OH already there, CH2Br already there. So what happened to this side here? Oh, sorry, CH2Br, from which Br you eliminated, right? So you have CH2. What is still remaining there? CH2, CH2, CH, right? CH2. So we have CH2, CH2, CH2 remaining there. So what happened? This Br, if it eliminate, these two alkyl groups get join, you will get another cyclohexane part here. So where you can able to see, in option D, this is a cyclopentane part, right? This is a cyclopentane part, not this option, because there is a cyclohexane is forming. You can see 1, 2, 3, 4, 5, 6 carbon, that is in option B. So first case, the ether bond breaking, or with the CO bond breaking, with which HBr. Second one, Wood's reaction. The alkyl group, two haloalkane when come in contact, the halogen eliminate, the alkyl group join. Next one, question number 2020, again, the decreasing order of reactivity of the following organic molecule towards the silver nitrate solution is. You can able to see some haloalkanes are here. What happened when haloalkane react with the silver nitrate dear all? That will take the AgCl, that AgCl form. So it's like first you have to remove the halogen, and this is a carbocation, halogen, carbocation, because this Ag take this chlorine, right? Ag will take the chlorine, you will get the carbocation. So this is another carbocation, another carbocation. Which carbocation is more stable dear all? Then they will undergo the reaction faster, yes or no? So you can able to see, you know, this is cyclopropene, cyclopropenyl carbocation. It's stable and it's having a what? Aromatic character. It's an aromatic compound according to Huckel's rule. So here dear all, careful, this carbocation you can able to see, this is sp3 carbon, this is sp2 carbon, this is again sp2 carbon, just like a allele pattern, right? Anyway, the compound is what? Aromatic, you know, it's stable, one aromatic compound stable. So after removing chlorine here, what about this case dear all? This is also a cyclopropenyl carbocation, cyclopropenyl carbocation. It is also stable due to resonance, but there is a methoxy group. You know, methoxy is an electron donating group. As I told you dear all, electron donating group if there, they will stabilize the carbocation more. So among A and B, which is more stable carbocation, B is more stable than A. Next one, what about this carbocation? It is a secondary carbocation, whereas it's also a secondary carbocation, but there is a nitro group. Nitro group is an electron withdrawing group dear all. Electron withdrawing group decreases the stability of carbocation. So C and D, when you consider, C is more stable than D. So what is the correct answer dear all? Is aromatic, so more stable, okay? So B greater than, A greater than, C greater than D. B, A, C, D, which is the option? Option A is the correct answer. Next one, which of the following, question is from 2020, which of the following compound will show retention in the configuration with the nucleophilic substitution of OH minus? There are retention of configuration is in SN1 mechanism. So which will undergo SN1 mechanism faster? That's a question. So first compound, let me consider CH3, CH, C2H5, then we have CH2, CH2Br. As I told you, the first step in the SN1 mechanism is remove the halogen, make the carbocation. Dear all, at present situation, what this carbocation, it is just a primary, right? Because the carbocation connected to one carbon. As I told you, if you get a primary or secondary carbocation through SN1 mechanism, please check it whether there is a chance to get tertiary or not. Is there any chance? Yes, dear all. Please transfer the nearest hydrogen to this carbon. That's called what? 1,2 hydride shift. If this hydrogen leave to this carbon as H minus to the CH2, it becomes CH3 and the C becomes C plus. So you will get CH3, C plus, C2H5, and then we have CH2, CH3. You'll get here CH3 is the product, right? Now initially it is primary, now it is what? Tertiary. Initially it is primary, now it is tertiary. What's the case, dear all? Where the OH minus prefer to attack, where the nucleophile OH minus prefer to attack on this carbon. So when you add the OH minus here, you will get this OH minus on this carbon. You will get CH3, COH, C2H5, and then CH3. So where it is that? Where it is, tertiary alcohol will form. What about this carbocation? Here you will get only secondary carbocation. Here you already got tertiary. Here if you remove the halogen, you will get, there is maximum chance to get secondary. Here if you remove the carbocation, you will get benzyl. Benzyl is there because C6H5C plus benzyl, and is secondary also. There is no chance to get tertiary. You know, tertiary carbocation is the most stable one. So A prefer to undergo the reaction faster. So let me remind you once again, if it is an SN1 mechanism, first step you have to remove the halogen. If you're getting a primary or secondary carbocation, check whether there is a chance to get tertiary or not through this kind of shift. Okay, next question. 2019, dear all, which hydrogen is compound E is easily replaceable during bromination reaction in presence of light. You know, bromination in presence of light, which means what? Substitution reaction, right? You know, substitution is happen mostly on an alkane chain, and also substitution reaction, you know, it's happened through free radical mechanism, right? Free radical mechanism. Dear all, from which carbon you can take the hydrogen? From the alpha, beta, gamma, or delta? From which carbon you can take hydrogen easily? Remember, if you remove hydrogen, it should get stability. Then only they're ready to release that hydrogen. Let me take hydrogen from this carbon, dear all. Why I'm taking hydrogen from this carbon? Because if you remove hydrogen from this carbon, you will get what? You know, it's undergo free radical mechanism. This is just like a allyl group. Yes or no? sp3, sp2, sp2. What is allyl group? sp3, sp2, sp2. Allyl, you know, allyl carbocation, allyl free radical. These are more stable. So you should take hydrogen from this carbon preferred because it's giving more stabilized free radicals. So dear all, option I'm taking hydrogen from gamma because it's allylic one, a gamma hydrogen. Okay, next one, question number from 2014. For the compound CH3Cl, CH3Br, CH3I, CH3F, simple question, the correct order of increasing carbon halogen bond length. Where you can able to see carbon, this is actually C with the F, C with the Cl, C with the Br, and C with the I. Where is the greater bond length and least bond length, dear all? They need the bond length order, dear all. You know, fluorine connected to carbon. You know, fluorine is the most electronegative element and the smallest element. So once they make the bond, it will be very strong bond. So stronger the bond, the lesser the bond length. Where bond length is less, right? But iodine, you know, fluorine, chlorine, bromine, iodine, down the group the size of the halogen increases, bond is weak in the sense bond length is more. So more bond length is for I, Br, Cl, F. Option A is the correct answer. Right, next one from 2010. Consider the following bromide. What is the correct order of SN1 reactivity? You may have seen many questions from SN1 reaction, dear all. Yes, dear all, in SN1 reaction, first step you have to remove the halogen, make the carbocation. Remove the halogen, carbocation. Remove the halogen, make the carbocation. Can you able to say what type of carbocation is this? It's just a primary, right? It is just what? Primary carbocation. primary carbocation. What about this one? This is CH2 and this is what? CH and CH2. What is this group here all? This is sp3, this is sp2, this is sp2. This is a allylic one, right? Yes, it's a allylic carbocation. What about this carbocation? It can form maximum secondary, right? Maximum it can form because this carbocation connected to one methyl group, one CH2 group. So, right? Yes, it's a secondary carbocation. Which is the most stable carbocation, dear all? Allylic is more stable. Then which one? Secondary, and least is what? Primary. BCA is the correct answer. That is option A. So, right, why allylic is more stable here all? It can make resonance, right? Resonance stabilization, then secondary, then primary. BCA is the correct answer. Next one, the Woods-Fittig reaction. It was question from 2013 JEE Main. The Woods-Fittig reaction involves the condensation of, Woods reaction is used to combine two haloalkane. Fittig reaction is to combine two haloarenes. But Woods-Fittig together, that means it's a combination of one haloalkane with one haloarene. So one molecule of each of aryl halide and alkyl halide. Option B is the correct answer. You know very well. Now, elimination of bromine from 2-bromobutane. What is 2-bromobutane here all? This is the compound 2-bromobutane. When it undergo elimination reaction, what haloalkane undergo which elimination reaction? Beta elimination, right? What is the major product here all? If you use a strong base here like alcoholic KOH or etc., what is beta elimination? Halogen you have to take from alpha, hydrogen you have to take from beta. You have two beta. You will, I told you according to Zaitsev rule, more substituted alkene should be formed. So it's a major product. So let me take hydrogen from this one and I'm making double bond here. CH3, CH double bond, CH single bond, CH3. You will get a but2ene. If you take hydrogen from this beta, I have to make double bond here. I will get the product as CH2 double bond, CH single bond, CH2, CH3. This is but2ene. This is but1ene. Which is major product here all? But2ene is major because it's a more substituted alkene according to Zaitsev rule. So we will get predominantly 2-butene or but2ene. Option B is the correct answer. Next one, chlorobenzene. In the first part, the first question we discussed from this one, dear all, 2014 again. Chlorobenzene react with the trichloroacetaldehyde. What is trichloroacetaldehyde? Chloral, right? In the presence of H2SO4, what's the major product formed? ACE. Right, dear all, chlorobenzene when react with the chloral, we will get DDT, dichloro, diphenyl, trichloroethane. Where is DDT, dear all? Where is DDT? Option D. You can able to see here, dichloro, diphenyl, trichloroethane. That's a product. Yes, others are not DDT. Next one. Among the following, the molecule, 2012 question here all. Among the following, the molecule with the lowest dipole moment is, all are haloalkanes given here. You know very well the CHCl3, this compound, and the CH2Cl2, this compound. CHCl3, chloroform, this is the compound, and CCl4, this is the compound, right? Among these four compound, which one is lowest dipole moment? You know very well what is the dipole moment order of this molecule. They're all here. Chlorine is an electron withdrawing group, carbon is more electronegative. So here dipole moment all are adding up. It's having highest dipole moment, highly polar. What about this one? This chlorine, there is some cancellation. You can able to see chlorine, some cancellation. Here, in tetrahedral geometry, all of these compounds having tetrahedral geometry. In tetrahedral geometry, if all the surrounding elements are same, all their dipole moments, cancel each other. Where dipole moment is 0, it's non-polar. So, which one having lowest dipole among this one? You can able to say option D, C, Cl4. Which one having greatest dipole moment? We can see CH3, Cl, that is methyl chloride. Hope you cleared here all. So these are some of the previous year question from the chapter Haloalkanes and Haloarene for the JEE Main. So dear all, we will meet again with some more other chapter in the upcoming video. So thank you all. See you again. Bye all of you.
Brilliant Qatar, your trusted coaching partner for IIT, JEE, NEET, Science and Commerce tuitions with 10 years of excellence in quality training. Brilliant Qatar.